with respect to acoustic at omega at k equals 0. But they're always out of phase, but with different amplitudes. What else? We also discussed in a 3D crystal what kind of modes there are. We said the number of modes is equal to the number of degrees, number of dimensions, so the number of atoms in bases, and that acoustic modes are always equal to the number of dimensions. We also discussed transverse modes and polyton to describe them. Now I will take 2 seconds to compare something which maybe even shouldn't be compared, but it's good to have it clear. I know that every year there was somebody confusing a bit dispersion relation for energy and for the phonons. I mean, it's obvious, but okay, let's just see. En of k versus omega of k. So they are both defined within brilliant zones. K is within brilliant zone. We showed it for the energy. Also for the frequency, we derived it was from the dynamical mass proportion relation. This was here with displacement for I. What I want is this dependence, exponential dependence, which is A on IKR. And if I take K to be equal K plus some reciprocal vector to be in zone, I will get it as we already showed. This is 1, and we always remain with the vector within the brilliant zone. This is an old thing. Also, we can say that the symmetry is always conserved, keeping the symmetry operations of the crystal and time reversal, which gives you the same as for the energy. Then there are periodic boundary conditions. Conditions born from Kahneman, which gives you exactly n values in the brilliant zone. So it is also discrete. No? The same logic applies. I wasn't specifying any of this because it's kind of implicit. In the fourth one, actually, there is a difference. For the energy dispersion, this n is infinite. No? How many different bands? Energy bands, infinite. While for the phonons, there is n dimension times n atoms per base modes. This is a finite number. Well, both of them are actually analytic functions. Big functions. Okay. That's common. And actually from this, you will learn next semester the huge difference between electrons and phonons. One is fermion, one is boson. Because if you write, I'm not going to talk about it, if you write the energy of the phonon, it's it's equal n plus 1/2. It's quantized, h omega. And actually, this n depends on the k and the mode, which you have optical transfers of all of them, and this omega depends on k and s. This depends on k and also s. This is, and you can have as many as you want number of phonons. You can excite. You can put all the energy into one type of phonon. While in fermions, there is a limited number. You can have maximum 2 electrons of opposite spin at the same energy. So this is the distinction fermions, bosons. And they obey different statistics, Fermi-Dirac versus Bose-Einstein, but okay, I'm not talking about that. Good. Just to put things into context. Okay. Now, did you maybe derive for the system of different masses?
Yes.
Did you derive the dynamical matrix?
Yes.
Yes. Everyone? Okay, so let me derive it, and then I'll ask one of you to come derive the. I'd like to derive it with all the indices. I'm not sure you have all the indices.
Indices.
Do you have also indices for the atom in the base?
Yes, 1 and 2. Yes.
Where is it starting? Okay, I'll ask you maybe to derive the rest. I'll just derive the dynamical matrix, and then I'll ask you to derive. So, from the previous case, from the Newton equation, we started writing m times second derivative of displacement is equal negative sum of the force constants times u's. Now, I'm going to write the mass. Let me first draw what we are solving. The unit cells. Okay. One big and small. I'm putting at the equal distance because the springs are the same. Sorry? What? I didn't hear. Was there a comment? I didn't hear, sorry. I heard something, but not clearly what. And so let's call them all K, all the spring constants between the first neighbors. And then we can, this is a mass 1, mass 2. But in principle, we can have n atoms, let's say, m atoms in the base. So I'm using the index mu, or nu, for the atom in the base. Here I have just 2, but I can have 10 if I want. Who knows what you'll have in December. So I'm writing mass with an index mu. I don't care so much of the index of the cell for the mass, because it's always the same. It's periodic. Okay? And displacement, u, which depends on this, on the mu, which depends on the n, and which depends, oh, what else? And the alpha, which is direction x, y, z. Okay? So this is the cell index, Cartesian direction, how to call it? Direction. And this is the atom in the base. And it's equal to the negative sum of the J and beta, the alpha beta. Here is alpha. I used n here, so I should actually use n. Am I confusing you with this n? Because I put n as the index of the cell. I can do that. And u beta j, but also this one depends on all the atoms in the base, so I will also write the index nu for that. Okay. And let me define the displacement. The amplitude. Well, the mass of mu, but it depends on the alpha and mu. And then I omega t plus k and a.
Excuse me.
Yes.
I think in the sum we also need to sum over mu, and d also needs
Right,
mu.
right.
I think d.
No, I'm assuming the constants are the same.
Okay.
So I drew it here. So no, but the sum is true. Forgot. It's very hard to comment by name, I guess.
Sorry?
It's very hard to comment by name. Okay, so let's put this derivative inside and we derive. Okay, I'll skip a few steps with respect to the last time because we've done it already. And this is minus omega. Mu j beta. Is this correct? Am I missing something? I guess it's okay. And then we can divide by the negative, this is division, the negative square root mass of the mu atom, and this gives us the amplitude of mu alpha as a sum over mu and beta, so sum over all r. Again, I'm replacing the sum over j with the sum over r as last time. No, not alpha, it's mu. Mu and no, it's not beta, it's and the exponent and the amplitude. And now this is my new dynamical mass matrix. What am I saying? My God. Matrix. And we have this mass dependence explicitly in it. Is it okay? I mean, I think it's. But now, knowing this, knowing the ansatz, essentially all you have to know is the ansatz for the case with different masses. You can solve almost anything.
Yeah, you can at least find the matrix, then solving is another.
Okay, solving explicitly, analytically, yes, but you can come to the matrix at least, yes. You can come to the matrix and at least solve for some special cases. But this time you could solve everything, no?
Yes,
until the end. It wasn't
yes,
so difficult. I couldn't remember when you asked me, but it's actually. Okay. And now let's solve, maybe you want to come, and solve to find dispersion relation for the phonons in this case. wasn't clear.
Is it okay if I write this K as D, because I'm going to confuse it with that K later on. Because we have been using D.
Okay, fine.
It's fine.
Yeah,
Fine.
fine.
Just carefully, I was using this kind of D for the dynamical matrix. I was using different D for the force constant and different D, and this kind of D I use for dynamical matrix, but okay. I guess you guys know this is just the force constant.
So this is just the force constant because it's the same
In
now.
the first neighbors.
Yeah, in the first neighbors.
Here you are showing my second neighbor.
No, it's between, okay. So obviously they won't interact. I was saying like one cell to between cells. Between cells. So our answers will be like a little bit simplified here.
We have just two atoms. We don't have to use for the m atoms in the base. Super. Have you tried this one? Okay, good. You managed to look up to do.
I think it's I didn't get the final.
But you got the matrix. Okay, we see some. I mean, solving in the end, you get the second order equation, which.
So this is for, I'm talking about the nth cell here, or this is actually for general one. So this is our answers. We will start from here, and we just as we just now did, we have our the differential equation, which is m1. Okay, 1 mu the nth cell, the first base. The bigger one is the not the the bigger one.
Yeah.
Of the
It's easier
size
to-
ones, yeah.
It's easier to visualize. It's not important.
So
the
if-
volume doesn't enter.
Yeah, so if we expand the one that was just written right now, and we would get something like this. So this comes from, this is something like d alpha. Sorry, d nu.
The self.
The self
Force constant.
force constant.
Force constant.
And 2. This is for the
I think you could get the location and knowledge. Let me know how it's going and if you have a difficult. Yes.
So just
But the end is just the first step when you have the interactions between cells. But then you divide everything by E on the IKNA.
This is how to come up with this index.
Okay, here is the cell test. You just keep doing it. And
Yes, yes.
this atom will interact with the atom from n+1
Yes.
and with the atom in the same base in the n cell.
So it becomes E.
And this one, then you divide everything by E on the IKNA, and it just remains plus E on the IKA from the neighboring cell. And this one will interact with the atom from this cell, E on the minus IKA.
Yes, I agree with that.
So what is confusing?
Yes, the 2, 1. I know how to do the n minus 1.
What
plus
2?
1.
What for 2?
This index one.
2
What does
is
you
in the
put
base.
one.
This is number 1, atom number 1, atom
Okay.
number 2.
So when you're interacting, then you have 2, 1.
Yeah, I mean you have to specify both the atom in the bases and the cell. You understand this? Yeah? It's okay?
okay.
It's okay, good.
So I'm just going to tell like how do we choose like this specific indices. So right now we are focusing on cell n. Cell n includes this basis 1 and basis 2, which are like bigger and smaller, just to like make you feel that way. So the first one is for the equation for the first one, basis 1. So that means n cell and the first basis, and it is the mass of the that particular basis. So it is the self interaction, and self interaction it does with itself. So it is n and 1, its own location. So the other two interactions are given by this dotted line here. This dotted line, it does with the other basis of its own cell, that means cell n and the basis 2, and the other interaction it does with the second basis of the cell from which is behind it, that means n minus 2. Like similarly, the second basis, which is the base 2 of the n cell with mass m2, interacts with itself, second basis and n cell. It also it is given by the solid line here, solid lines, two solid lines, interacts with the base 1 from its own cell and base 1 from a neighboring cell which is forward of it. And all in all these things, like all these interaction strength are kept as constant. So we know that
Acoustic sum rule.
Acoustic sum rule. So over R. Okay, I'm not writing alpha beta because this is a single case. So let me just write. And n would be 0.
It should be threshold.
So
Yeah.
the acoustic sum rule gives us this. If it was not a one-dimensional case, we would also need to include the indices of the axis, x, y, z indices. But since it's just this, and the R is chosen depending upon how far we want to go, like what kind of interactions we want to take. Since we are just taking the nearest neighbor interaction, it will just mean d naught equals to 2d. 2d or minus 2d? It's 2d.
Yeah, it's minus because you chose this to be negative. This is you define them as minus k, let's say.
So we
The
can
base.
replace it here. So now I'm going to look at it because I don't want to make any mistake.
Yeah, fine. But also you can skip a step maybe. I mean, we still have to solve a longer one.
Okay,
It
so
takes more time.
I will do it for the first one, then the second one I will just take it
Yeah.
for granted.
Yeah, no.
So what we do now is I'm going to remove this right here.
You solve them both, I think?
Yeah, I made a mistake somewhere.
It isn't.
Yeah.
So we are going to take these answers and put it right here. So this is for the first one, second one. I'm going to put this one right here. Just like this.
I'll give you a problem. Simplest possible. But it's very useful because you can see the different modes along the propagation and perpendicular. So that's the homework problem. And oops, I forgot to print. Actually, I did print. I forgot to take it. To print. If anyone feels like it's on the printer, then it will be office. Yeah, if you solve it, if you don't mind going. I feel bad leaving the class.
No, I can't go there.
It's on the printer next to my office. You know where my office is?
Yes, yes.
And the printer is even further.
Okay.
Like, you can't. I printed this morning, should be still there. I just didn't pick them up. Should be 8 pages. I hope it's printed. Unless it doesn't print, but normally it does. Thank you. we can skip a few steps and come to the final.
Okay, you know what to do, like you just
Divide by I omega t by E on the I kNa. Divide by square root of mass m1 by minus. Okay, you can even go further. You can even go.
from here. I have directly written the matrix. So
This is already not very direct. If we have this one still dividing by this. You have, or you kept this mass all the time.
yeah, up until here, and from here I have directly jumped to the matrix.
What do you write over D?
D, because I've taken this side.
Normally you want to express omega square alone and put all the factors in the other one. Also the mass and the... You want to say omega is equal K over F, essentially.
Finally, I just multiplied with D. I just wrote the matrix just in terms of mass, and whenever I have to...
No, but normally D is in the matrix. Most mass can be out, but normally both mass and D are in the matrix.
So,
What is this minus?
this is 3, like number 3. Minus K, IK.
Yes, and minus?
This is 3, like
Ah.
number 3.
Okay. Oh, it's 3 now. So you're subtracting 3. Okay, sorry.
Similarly, like we
Yes,
can manipulate
yes,
this
yes.
and we can get a similar equation.
Check. And from here we can write the matrix. Maybe here.
So this is, if you look closely, it's in a nice matrix way.
Here, right, I'll write it here. Inside.
This U1.
Uh-huh.
So we can write a matrix directly from here.
Try to
It
put
will-
all the masses and these
it will-
in the
yeah,
middle.
it will just take.
And then solving it, I mean, one can get a bit, I mean, if you don't cancel everything right, you have too many terms. But it's easy to make a mistake, let's say. But I mean, this is already a good step to come to here. So for the U1, we have this. And this is for the U2. Good. Good. Thank you very much.
Okay, so this is our matrix. Now we can solve for specific cases.
Well, we can actually even skip that and solve right away in general.
In general,
Yeah.
okay.
I mean, to shorten time, but then in the end we analyze special cases. But this one is easy to solve. I mean, easy. It's, one can solve it and find the eigenvalues and eigenvectors. But okay.
Actually, okay, I will solve it because I did it individually. So.
Yeah, also, I mean, I said this, but it's actually quite easy to solve everything.
T minus m1 minus omega.
That's correct.
M2 minus
Yes.
There's something I missed when I was doing the question, and then what
Of the U
Yes, yes, yes.
displacement.
Yes.
Well, if you think on the mass, it's important. I'm taking that this amplitude has inside the right vector to be normalized, the U, but mass is very important. You have to have the mass because it's
Yeah,
different.
of course, finally I came up with mass exactly.
Good.
But I had over the square of M1 over the square.
How then could you get to it? How could you get to the masses in the end?
No, of course the masses would come from this.
No, but if you have different masses, you have to use answers. Yeah, it's, I mean, actually the answers has to be mass dependent.
Yes, they had mass masses.
No, not the frequency, the displacement, U.
Yes, they use.
The U has to have mass dependence if they're different mass. So I don't think it can be correct if you took U just the amplitude times it has to have, if it's different masses. If it's the same mass, I don't care, it's the same.
Oh, so that's the one, that's the original showing the test example.
Yes, and the U's obviously are not the
Okay,
same.
so this is our matrix, and I'm just trying to diagonalize it. So minus lambda. So lambda will be omega square. I didn't want to use omega square. Then it would be
It's the same.
yeah. So later on we will find that. So you know what is this, right? This is u1 u2 equals to omega square u1 u2. So this is we are trying to solve this. So this, so this is cos k.
But where is the cos and K? Okay. You're still writing it, sorry.
So that will be root m1 m2 2 1 plus cos ka. I think we can expand this in half angle or
And
maybe,
it's equal to 0?
yeah. So this is our quadratic equation, and now we have to solve this. Can I?
So this part here is exactly 1/2 of this. No? So we can actually,
actually
it can be cancelled. I mean, not cancelled, it will be.
From this step, okay.
Ah, but this
However,
is.
when I reach such a step, I just carry on this part. Then it looks like I guess I will.
But you have a mixed, you see, and one and two mixed. You lost that.
Yes, I did.
Uh-huh.
I missed that. However,
Yes.
on reaching this step, yes, it's not exactly the same.
Yeah, okay.
However, this kind of units with omega squared and so on, I carry on with
Yes.
and I bring it here.
It can be done, yeah. So you have actually, yeah.
And then what I did was,
No, actually, it has to be able to be factored out. No, if it's the same mass, you can put m omega squared. This way you cannot optimize it.
So, right?
Let me see if it's the same one. Here. Well, I wrote this as sine square Ka.
Sin square.
You have here 2 minus 2 cosine K. These two. Okay, these two terms.
Okay, you have like taken
It's
common,
1
yeah.
minus cosine
So
Ka.
let me just do it right
Yeah,
away.
it's 2 sine square Ka half.
So if you take common, it will be 1 minus.
Yes.
So we can now convert it into half angle formula.
Yes.
So which will be equal to 1
Yeah, the rest is the same.
minus Ka by 2.
Yeah, we should rush because we have also second thing to solve. And I wanted to do also experiment. Are you solving for lambda?
Yes.
Then
Oh. Oh, sorry.
But it's very hard to find that. I'm not saying it's impossible. This is not a common way to find that. I mean, normally you factor it out here. You don't have to pen those different. It's hard to read the coefficients. I mean, it's possible. I'm not saying it's impossible.
I see what I'm saying is that if I do it like this,
Yes.
then it's going to clear then you can say into image.
Sure.
Is equal to this. Meaning that the determinant of such a thing should be equal to this. I mean, that's what
But then you don't have the same I mean, lambda, what you call here, because it depends on the column. It's not the same math.
That's what it's.
Okay, so it's complicated. You cannot find the eigenvalue. You understand? It should be the same. You can always do. This is the basic way of finding eigenvalues and eigenvectors. Okay.
So now.
Very good. So, if at gamma k equals 0, what do you get as eigenvalues?
Okay, so if k equals
If
to
it's
0.
0, you get plus minus d, the same term. No? So omega squared 1 is equal to 0, because if the sign is minus, I'm rushing a bit because we have also to solve the second one. And this one is 2 times this. No?
Okay, 2
So
times.
at k equals 0, you have here and 2 times, you call it d, no? Okay, what I had, okay? 2 times. This can also be written as reduced mass, but okay, it's the same thing in the end. And for, yeah, zone boundary,
So for k equals to pi by a, it will be very easy one.
this one becomes 1 over m1 minus 1 over m2. So you get two limits. Mass 1 is larger than mass 2, let's say. So mass 1 will be lower. What is common is that acoustic mode has much stronger dispersion than optical mode. Optical is much flatter usually. So that's why I'm plotting it like this. 2d over 2.
Sign the exponent.
And
Exponent sign.
okay, so now we don't really have time. We should derive, but I really want to solve the other problem, which is completely new. You have to derive the eigenvectors for this one. Can you do it very quickly?
Yes.
Okay,
So-
or it can be also for you as exercise. Here it's acoustic and optical, typical in phase and opposite. So it's easy at k equals 0. At the zone boundary, it's a bit less obvious. What is the matrix at the zone boundary?
2 by 2d.
So for omega 1, I'm writing for omega 1, I'll get determinant 0. Omega 1 is m1, yes. I think it's 0, 0, 0, and then here it's
No, the matrix is diagonal.
yeah, I'm just saying when you want to find the eigenvalues. So it will be, is this something of this type? And this can give only one type of eigenvectors, no?
Excuse me.
If you have, I'm rushing now, sorry.
It was me.
Ah, sorry, I look at you because you moved.
Yeah, I got the same thing.
Yes?
However, how much?
Can you solve the eigenvectors?
Actually, ma'am, since it was diagonal, I just thought like it would be independent of each other, and I didn't like what the actual value.
This one has to be 0. Because this term is 0 for the pi half. This one is 0. This one is non-zero. If you take determinant. So actually, the second one has to be u1, u2. This can be anything, u1, but this one has to be 0.
Okay, I thought like they would be like completely independent of each other, like this.
Yeah, but if you try to solve for one mode, so each mode is different.
Yes, ma'am.
So in one case, you will have that this guy is moving, this guy remains. And then this guy, okay, for this one, this guy is moving, this guy remains, no? This is one mode.
Okay.
The other mode is that the other one is stuck. So this is for acoustic, and for the other one it is this. Sorry for rushing. If you have questions, this is basic eigenvectors. I mean, it's nothing.
Yeah, I have to do this.
Yeah, I mean, we did a lot. It was 2 days homework and you have a lot. And the rest is very similar to what we did. And if the masses go to each other, we get just the same case what we discussed last time. When we took the limit of different springs becoming the same. Thank you, Nishan. You should be a teacher one day. You really like teaching. You're good at it. You like teaching, you're good at it. Yeah, I hope you will get the chance once. Okay. I really want to cover the case of the neighboring, the second neighbor. You have any questions on this? But not technical mathematics now. We can discuss easily mathematics afterwards if there is a problem. But, okay. Now let's solve the case taking into account the second neighbors. And I actually want to introduce ferroelectrics in that example. We don't have so much time. We'll probably go a bit over time. Okay, again, a linear chain, unit cells. And now we say that actually up to the second neighbors, there are interactions. Peter, you said you derived this?
No, I derived just the equation.
Okay, count that. Yeah, you showed me 2 points I need to have. I'll try to come to the form that I have so it's easier to realize. We can start from the dynamical matrix or from Newton equations.
So the it was M U N double dot. This must be equal to D naught U N plus D A.
Actually, there should be a sign minus.
D A U N plus 1 plus D minus A U N minus 1 plus D second nearest will be
Yeah,
2A plus 2 minus 2A U N
Minus 2.
minus 2.
Okay. Well, we can maybe write the acoustic sum rule. Or
So it will be D naught plus
And d of A and d of minus A is the same.
Same.
Come on. Excuse me.
Must be 0.
First, the second nearest neighbor include just for n. The second nearest neighbor is just for the atom at position n.
This one is our starting one. Interact with the first and with the second. With a different force constant.
Because when I did it, I did it for both n plus 1, both second nearest neighbor.
Yeah,
Ah.
you have to go.
Well, this was the whole thing. Otherwise, it's easy.
Yeah, you go to the second year.
I mean, you can solve in the first neighbors, why not? But
No,
that's already done in the
I'm
class.
saying I'm taking the second nearest number of n plus 1.
A.
Second nearest
So you went to n plus 3.
Yes, n plus 1.
Oof! I understand. You went to the third neighbor then.
This is not third number. If you take it according to n plus 1, this is not third number. This is n plus 1. This is first second. So I consider these three atoms.
You went from, you centered your system at n plus 1 and took the second neighbors from there.
No, n plus 1 and n minus 1.
So n is your atom.
Yeah,
You
I
went
did
from-
it for n. I did it for n plus 1. I did it for n minus 1. Both first and second.
No, no, they're both first neighbors.
They're both first neighbors.
These are both first neighbors. I'm not saying how many neighbors. Nego what order of neighbors. So these are both first. They are equal
This
distance.
n,
It's just what you call second neighbors. Because it's a second shell of neighbors.
I remember that when you gave the assignment, I asked you if it is just for the atom, and you said no, that you should do it also for n plus 1.
no, in this
There
case,
was
it's
no-
it has got single basis. I think you are not confusing with cell and
I
basis.
think there was a misunderstanding. Sorry if I caused it. Okay, let's say this is something important. We'll keep it. Okay. I actually
No, no, no.
affected out. Okay.
How
DA
come?
and affected D2A.
Why is there no this amplitudes?
We have just one dimension, so it doesn't depend on x and y. And we don't have basis. We have just one atom. So there is no dependence on alpha and on mu.
No, I'm
mu.
saying amplitudes. Okay, he like took
Because it's the same, you can divide.
No, but aren't the amplitudes different, like n,
No.
n minus 1, n plus 1?
Yes, that he put as a phase factor.
As a phase factor.
I mean, here, divided by, he skipped a step which I'm grateful for because we are rushing. He divided by IKNA, everything, and this is what came out as a difference. He didn't go step by
No,
step.
no, I'm saying like he took the amplitude as the same, like U double dagger, U
Yes,
double
here.
dagger.
And then he plugged in this.
So that was the answers you gave that? Did you give that answer?
I mean, this is the normal one. If you have the same mass, this is the answer.
Okay.
If the same mass, why? You don't have to keep the mass in the, it's the same. As soon as you have one atom per cell, you know it's one mass. Yes. And now we can write this one as the double angle in terms of this one and cosine k half. Maybe the new line.
New line.
I think people are getting lost. And we can put the positive frequency. So multiply by -1. Everything. And now we can factor out 4 sine ka.
That's square.
It's square, sorry.
Very good. Okay. Did you all understand? We skipped a few steps, but I think the basic math was there. Is it okay? How Ravindra came to this expression? Okay. Now the difficult part starts. We have to write conditions for the stability. Meaning we want to know when omega squared is larger than 0. This is our first condition. That is d of 2a Robin,
No.
stay please. Minus 2 dA plus d2a. Okay. And then we want to get from here conditions when omega squared is positive. Here we have minus sign. This is always positive. This is always positive here. So in the case when this is 0, this part, d of a has to be negative.
Negative.
So let's write the second condition. We are going a bit upside down. Okay. And the third condition, if I take the maximum value of the cosine as 1, it's the worst case. Then I say that dA plus 4d2a has to be negative. Is it okay? If this is in between, it's in between the two limits of just this term or this one maximum. This is the way I used to write. Here out now this way. Plus 4 2a. Okay. And now just to solve this, to find the d2a dA. And maybe Ravindra would still come to solve this. It's not difficult, we just have inequations.
This means we have to...
The first one, the A has to be negative. In this
You
graph,
can like draw it graphically and find the region of interest.
yes. Now we are in the space
The
of d2a
whole
and
region.
d of a. We will express one with other.
The
So
whole
this will
region.
be in this region, right?
Yeah, the whole region.
So, okay. What I was drawing until now is to blacken the part which is not good, or we can indicate the part which is good. We just decide and then down. We want to indicate what is allowed.
Now we have to check for this
Okay.
condition.
So this is allowed.
Yeah.
No, maybe it's easier to go for the other one. I
Yeah.
think.
And
So this is not allowed.
Not allowed, yeah.
Fine. Okay, now let's draw this part. You can express d2 of a.
We can express that as an equation of line and then
Yes, exactly. Question of line.
Yeah.
y equals n express equal to 1 over. Y equals to 1 by 4 x.
D2A is also we can express it as 1 by 4 dA, right? So 1 by 4 means slope negative means we have to take
No,
passes
four
through
x.
it.
This is
Passes
x.
through it.
So 4 of these and 1 of these. So this is 1 point and 0.
0.
So it has to pass through this
Pass
line.
through 0.
Okay. So it is this line. D2A is equal minus 1 quarter dA.
dA.
So this is, it has to be smaller than that.
Smaller than.
So this is allowed, this is not allowed. Yeah. And the other one, the last one, D of 0 has to be positive. The whole thing, which means that dA plus D2A have to be negative. Which means that D2A,
dA is
it's always inequality.
inequality.
No, it has to be, yeah.
So this
No. D of A plus D2A have to be smaller than 0. D2A has to be smaller than D minus D of A. So it is this one.
This one.
Oops, it's very hard to go to 0. Oops. And this one is D of 2A is equal minus D of A. Doesn't bring any new condition. We are already like in the forbidden region, so this is the part of space which we can use. D of A can be only negative, but small range of D2A allows positive values.
So we have to consider only the reason this
Yes.
reason.
Okay, now I will go and discuss a little bit the case. Thank you. Very good.
Excuse me.
Yes, ma'am.
I know how to sketch the inequalities and so on, but what does it really mean to ask for the conditions of stability?
That the frequency is positive. You know what is frequency?
Yes.
Okay.
So
Now
stability is basically frequency positive. Okay, thank you.
Now I will discuss that.
Can you plot the frequency and then look for the...
Yes, we will. We will. So, but I will
excuse
go.
me, why omega squared? Because if omega squared is greater than 0, it means there is a possibility of omega being negative.
Okay, it's easier to plot. It's easier to plot because if you get, it gives imaginary. You will see. It's easier. I'll come to that. I'll just come to that. You'll see. So let me show. Oh, we don't have the discrimination with blackboard anymore. Sorry. I'll write it here. Okay, let me draw it for the case when D2A is 0. This is what we know already. I will draw omega, not omega squared now. Cool. So what we have is a normal it's easier in 1D. This value is what? The 2dA of M. But then, as I start introducing this one, there is a part which will start changing. so strongly. We will always come to the same value at the zone boundary, because this one will give 0. But this is the effect of adding D2A.
Excuse me.
Mm-hmm.
I thought that the basic part is when D2A is not equal to 0. Otherwise, if it's equal to 0, then we are still considering the second nearest neighbors.
Okay, I'm trying to show the effect of D2A. So I go from the plot where D2A is small or 0, and I start increasing it. So this is the plot, the shape of the plot with D2A non-zero, but still satisfying these conditions. So in this allowed range, somewhere here.
Is there some problem with the signs because it's always negative in this case?
D of A is always smaller than 0. You remember what we derived?
Yeah.
And this guy also we have a condition.
Sorry.
So you have to, this is solution when you are well behaved due to second neighbors. Fine, what to do with that. But now let's see what happens when we are just at the border. When I'm just at this condition, just this one. Let's try here. Omega. So if I take D2A to be equal exactly -1/4 of dA. And the dispersion I get is -4/m sine square Ka2 dA. This is equal -dA cosine square Ka, which is exactly dA times sine square Ka half. You can factor out dA. And I get sine to the power 4 Ka half. I can plot omega. Okay. All this sine square gives a flatter range region around 0. It's not anymore linear, it's like k square. This is even as k to the power 4. It's very, very smooth. Well, not quite symmetric in my drawing, but it's flat. What I want to emphasize, it's kind of flat here. No, but this is, sorry, omega is sine square. Yeah, I was confusing what I'm plotting, sorry. Omega is sine square. But then let me see, if I just go by small delta in the region which is not allowed, what happens? I go by delta, and I'm wondering what happens. So, maybe here, I don't know. D of 2A is equal -1/4 D of A plus small delta. Now let me derive the square equals -4/m sine square of K half D of A minus D of A cosine K A plus delta four times I think I did something wrong. So you'll get the first part, which is the same as before. N square cubed of Ka half. I don't think this is correct what I have here. I was changing something, so you will get a part which depends as 4m.
Sine Ka.
Yeah, I'm getting the sign wrong, I think. Just a second. Yeah. Okay. This should be negative. Yes, this should be negative. 4m sine square Ka half cosine square Ka half times delta. And this is equal minus 4 dA over m sine power 4 minus 4, and this is 2 times. This is
Delta by m sine Ka.
sine Ka squared. And it's
Four
2.
is one.
Okay.
Delta by m.
Yeah, okay. Good. But dA is negative. So this term is actually positive. And here we have a sign minus. So if I plot with omega, I have a contribution of the negative side. This is what means to go in the forbidden range of the values of the force constant. And I'm plotting sine square omega, so it's like sine. It's hard to plot it on the opposite. Here it's flat. Something of this type, which depends on delta, so it's probably smaller in the amplitude. I'm just giving qualitative picture.
The first part is positive.
Yes.
The second part is negative. So shouldn't we talk about the relative strength between the first and second part? Because in first part, sine
Sure.
is to the power 4, so it is.
Sure, I'm
less, but
just
in
giving qualitative. Because as soon as you go negative here, you have a problem. Here you have enough space to go a bit negative.
Mhm.
Here you're close to 0 for quite some range of frequencies because it's a sine square. And this is sine K. Sine K goes much faster than sine square K. Changes the value. So in this range, region here, you will have a problem. And this in fact results. Now I'm just plotting something caricature to some kind of behavior of negative frequencies. You make it notes here. So I can plot omega squared. And what does it mean omega squared is negative? It means that I can write omega is as two numbers, I, B, and then I put for the displacements U proportional to the IKA. No, let's not call it A, let's call it alpha. Sorry. Which is plus I omega t, which is IKA times EI alpha t, which is fine, but times I minus beta t. Now, if beta is positive, sorry, I don't have much space, so I'm writing like this. If beta is positive, we have damped oscillations. But if it's negative, you have an exponentially growing amplitude, which kind of destroys the crystal. Might be the sign of melting, might be. So this is breaking of the harmonicity, where we assume small displacements around the equilibriums. Here, omega is complex number. And actually, this kind of behavior of dynamical instability, which is, okay, I can write the definition of dynamical instability. Process which brings regular repeating motion to an end. And this is very often a sign of phase transition. Which you can study in more than one way, and it's critical phenomena in the harmonism of Wilson, or in the mean field, or the Landau expansion of energy. You will get to do it, don't worry. But what I wanted to say here is that this can actually, when this happens, you get a new mode occurring, new displacement. And in the barium titanate, as well as in some other similar materials, what happens is that you actually reach one displacement. I will maybe draw let me draw the displacement right away. So this can be a cubic cell in a perovskite structure. The tanium is within an octahedra of oxygens. So this is the barium atom. And then there are oxygens on all the faces, forming an octahedral. This is on the top and on the bottom. And barium is at the edges. And what happens here, how many modes there are? How many foreign modes are?
Definitely 3.
in three dimensions. We have 5 atoms, 15 modes, 4 modes, or 3 acoustic, so 12 optical. And there are 4 different types of displacements here. One is all oxygens go up and the barium goes down, also oxygen. There are 4 different optical modes, but then each of them can be in 3 directions, 2 transfers, 1. So that gives for 12 modes. I'm just noting one of them, not to take too much time. But when these modes occur as an instability, the electric field due to ions, neighboring ions, is so strong, because these are ions here, that actually it doesn't allow crystal to go back to the initial position. It remains stretched. So in the equilibrium, it can be a paraelectric. No dipole moment in the cell. Without the field in the cell, whatever. But then when you freeze this motion as an instability, which occurs as an instability, you become a ferroelectric. And there is a whole group of these materials which have a permanent spontaneous dipole moment due to this displacement of the positive ion and oxygens. They are not in the same plane anymore. They're displaced. And they occur this way as you change temperature. So this change, when they took d of 2a equal minus 1/4 dA plus delta. This delta comes to temperature. So you actually have a phase transition into a ferrophase as you lower the temperature. Any questions on this? To be more exact, in this material, it's not happening in this point like this. It is happening due to softening. I mean, this is a generic example, 1D example. No, it was the simplest possible. This happens in reality due to softening of transverse optical modes, so actually just one mode. So what you have you have all the bunch of modes, optical modes, 3 here, and then optical, many of them. And one of them starts going down in frequency. Goes down, goes down. This is the influence of temperature in barium titanate. It's called softening of the mode, which means lowering of the frequency. This is a hard thing to follow. When this frequency starts going down, when you go something like this is called softening of the modes, reducing the frequency. There's also something called hardening, but okay, we won't go into that. There are also different kinds of instabilities, but okay, let's not go into details. I just wanted quickly to cover how phonons can be measured. I have no time to give you everything, just a flavor of it. Any questions? Neutron, inelastic, scattering, in the beginning of the class, I forgot to mention one difference between the energy dispersion and the phonon dispersion, which is the typical values in EVs. Do you know the typical values of the phonon branches, I mean the dispersion bandwidth? Are we in hundreds of millieVs, or 1 millieV range, or 1 EV, or 10 EV? Do you have the feeling of it? I think Nadia mentioned this in the Born-Oppenheimer. Usually she does, at least. Okay, which one is larger? Is the typical dispersion of binding energy of electrons in a crystal, or phonon dispersions?
Phonon is, I think, smaller.
It's much smaller.
Much smaller.
Because you know that ionic, energy curves are just within. This is electron holding, and these are the phonon, the ions or phonons. So they're like tens of millieVs. While electrons are on the scale of EVs. Can be 10 EV binding energy or something. Okay. Neutrons are neutral. They don't interact with charged species. That's good. Do you know what inelastic means?
That loses energy.
So we don't conserve energy anymore?
No,
Okay. We don't conserve energy, kinetic energy is not conserved. This is what it means. And this can be done on the tabletop or big singletrons. Fast neutrons are the energy of 1 EV. Slow 0.01 EV, so you can really cover the whole range of phonons. And what we can write here in general, the energy, the phonon energy in the crystal will depend on the K vector and the mode. Mode I'm defining as S, the phonon mode, as H omega Ks times N Ks. We didn't derive this result from condensation, where you have to assume creation and annihilation operators, and you come to this. It's a quantum picture. And after the neutron passes through the crystal, you'll get Ks dependence, omega Ks, but you have a different number of modes in general. So it can excite 10 modes of optical, transverse optical, mode 1 or something of that type. But this is kind of a complicated picture. I can also write that the energy after the passage of the difference between the energies after and before neutron was interacting is equal to the sum plus minus sum of a Ks let's call it delta n, which is the difference of these two, n prime and n, Ks plus 1/2. And this plus minus depends on what?
Whether the energy is gained or lost by
Yes.
the neutron.
By the neutron or by the phonon, by the crystal, it's the same thing. So neutron can excite the modes in the crystal, give rise to new phonons, new types of vibrations or new occupation numbers, how many you have of a given mode. Or it can take the energy, go out with faster than it came, by absorbing the energy from the crystal. And it just obeys a simple conservation laws, but let me write it in a one phonon case, not to complicate too much. So I'm assuming, and this is the simplest case, if I could excite only one phonon every time, I would know everything. But normally it's not that simple. You excite many of them. This is the energy of the phonon equal the final and initial energy of the neutron plus h omega k. I can write also the S, but it's one mode. And this is absorption of a phonon from the point of view of the neutron. Or it can be which is emission of a phonon. So this is the energy conservation. It is very straightforward. The second law is the conservation of crystal momentum. Our phonons do not have momentum. No? This is something a bit tricky. But we can assign a value h times k to the phonon. But it's not the momentum of the phonon. It's just an analog. So you excite a phonon at a given k, and you can find energy. But it's not momentum of the phonon.
Excuse me.
Yes.
Just the thing about the wording.
Yes.
Like there isn't anything like phonon, right? It's just the
Excitation.
Yeah, excitation. Because even though the ions are being excited, they are not phonons. They are.
And that's why it helps to go to quantum picture, quantum derivation. There you really derive it as a excitation, as a vibrational mode, as a particle. It comes much cleaner than what we did in a classical picture. It's a bit abstract.
So like since it's not a thing, like we can't actually assign momentum.
Yeah, there is no momentum of the phonon. But there is a crystal momentum.
Yes.
I can just add h bar in front of it and use it for the conservation law. So this is momentum of the neutron, final, which is equal to the initial one. So this is the part of the phonon. It absorbs the phonon of this energy. And it can also be like some crystal reciprocal vector. Or in the case of emission, finally I can write the two of them combined. This is mass of neutron, to be sure. Plus h omega. And now omega depends on the k, which is equal to the difference and the other equation. So we always have two equations depending on the absorption or emission of the phonon. This can be written like that. And what they actually measure is this difference of the phonon energy, of the neutron energy, sorry. And as a function of momentum, I think it's, sorry. Here it is. And here it's how many events you get as you change the energy difference. So we call it number of counts. How many events? At what energy? So you have something at this energy, you get a very sharp peak, let's say, but then you get much more dispersed peaks. And it's not easy to analyze this type of results. As long as you're in one phonon case, it's kind of trivial because you will get one peak. But then you get a whole bunch. This is coming from the background intensity. But what is interesting is that this width, I think I mentioned already, is due to anharmonic effects. Yeah, this is very quick. We are really late, I'm sorry. Anything else? I won't talk about Raman, there is no way. I'm not going to do that. Any questions?
What is that extra at G?
That you can always lose energy on the lattice.
Okay.
It's not. And here, this is all in assumption. Yeah, this is one more thing. I didn't talk about it before. We assume harmonic approximation. And it means that if you have a phonon at a given eigenfrequency, it just keeps but within the frequency. But in reality, they are a bit anharmonic, and they can interact. So two different phonons can interact and cause a third phonon. This is what we are not considering. I hope you will do it next semester. And gives rise to club system. But okay, this is just something interesting and nice, but we are not addressing it at all. Any questions? Sorry for the time.